5, 4, 3, 2, 1.
In the dead silence of the morning, at 5:29:45 Mountain War time, the Jornada del Muerto was bathed in an intense flash of a light that man had only seen from the stars.
Not be the same. Few people laughed. Few people cried. Most people were silent. I remembered the line from the Hindu scripture, the Bhagavad Gita. Vishnu is trying to persuade the prince that he should do his duty, and to impress him takes on his multi-armed form and says, "Now I am become death, the destroyer of worlds." I suppose we all thought that one way or another.
But there's more to E equals mc squared than atomic bombs. The recognition that mass can be converted into energy made it possible to understand the source of energy of the sun and the stars. Still a mystery in Einstein's day. It also paved the way for the exploration of the mysterious realm within the atom, and the discovery of a whole menagerie of new particles, created from pure energy in powerful particle accelerators. Let's ease our way into relativity with some common experiences. If you are traveling in a car on a smooth, straight stretch of highway, there's no sensation of motion at all.
You mean I could read a book, pour a drink, flip a coin, and everything looks and feels the same as if the car were sitting still?
That's because relative to the car, you, the book, the drink, and the coin are not moving. Notice that this works only if the car is not changing direction or speed.
So if the car accelerates or turns, pouring that drink becomes a real problem. Oh, but constant motion feels just like sitting still.
And if you want to know what it feels like to move at 1,000 miles per hour, just look around. Because of the Earth's spin, we zip along our time zone at a speedy 1,000 miles per hour. And because of its motion around the sun, the Earth carries us through space about 67,000 miles per hour. And because of the motion of our solar system, about the center of our galaxy, we are moving at more than 500,000 miles an hour. But it's not enough to ask, how fast am I moving? We must ask, how fast am I moving relative to some other thing? Let's make up a simple rule that allows two observers to agree on how fast something is moving. We begin at a moving walkway at the airport. The walkway is moving at a brisk 3 miles per hour. So, if Susan simply stands on the walkway, she is moving at 3 miles per hour, relative to Sarah, who is standing still but not on the walkway. If Susan walks on the walkway at 3 miles per hour, she can accurately say she is walking at 3 miles per hour. But Sarah sees her moving at 6 miles per hour. And if Susan walks against the walkway at 3 miles per hour, Susan can still say she's walking at 3 miles per hour. But now Sarah sees her as standing still, 0 miles per hour. So our first conclusion is that two observers can simply add or subtract their speed with respect to each other to any measurement of velocity they make. This idea is the basis of classical relativity. Here's another scenario. Suppose there's a truck moving down the road at a constant speed of 50 miles per hour. On the back are a baseball pitcher, a catcher, and their pitching coach, armed with a speed gun. As long as the truck doesn't speed up or slow down or hit any large bumps, they can conduct pitching practice just the same as they would on the baseball field. And when the pitcher throws a 100-mile-per-hour fastball, the coach's speed gun will read 100 miles per hour. The ball is indeed moving 100 miles per hour relative to the pitcher, the catcher, the coach, and the truck. But suppose an observer standing by the side of the road clocks the speed of that same baseball. What speed would this observer measure for the ball? Well, the ball would already be moving at 50 miles per hour when the pitcher was just holding it. So this observer would measure a speed of 150 miles per hour for the pitch, the speed of the ball relative to the truck, plus the speed of the truck relative to the observer. The example of adding velocities, in the bullet and plane example, is classical relativity at its finest. This classical version of relativity, simply adding the velocities, worked perfectly well for centuries for describing horse carts and ships, or baseballs and trucks, even airplanes, and rockets and bullets. But the relativity of classical physics is merely a very close approximation to reality. At very, very fast speeds, classical relativity breaks down. But this wouldn't be clear until scientists began flying Sopwith camels and examining the nature of the fastest known thing, light. In the middle of the 19th century, it had been known for quite some time that electricity could be used to make a magnet, and that magnets could be used to make electricity. But the man who made the first color photograph, James Clerk Maxwell, unified everything known about electricity and magnetism in 4 magnificent equations. And these equations described an electromagnetic wave that would travel through the empty space at exactly the measured speed of light. And in fact, this wave was light. According to Maxwell, light was an electromagnetic wave that moved through empty space with a speed of 186,000 miles per second. But from the standpoint of relativity, the question naturally arises, relative to what? The equation seemed to say that light moved at 186,000 miles per second relative to everything. This was a dilemma facing the physicists at the turn of the 20th century. If Maxwell was right, then light moves with a velocity of c, 186,000 miles per second, always. But if classical relativity was right, there is no absolute velocities, and the velocity of light should depend on who is doing the measuring and their motion relative to the source of the light. How could both be right? Either our understanding of motion or our understanding of electromagnetism and light were in jeopardy. The very foundation of physics was facing a crisis. a 26-year-old patent clerk named Albert Einstein would provide the way out of this crisis.
In 1900, Albert Einstein is a 21-year-old undergraduate at the Swiss Federal Polytechnic. That this young man will one day be synonymous with genius was something none of his professors would have predicted.
He would cut class. The professors thought he was a goof-off. As a consequence, Einstein couldn't get a single job after graduation. He even thought about switching fields and selling insurance. Can you imagine opening the door one day and there's Albert Einstein selling you life insurance? What a waste. Einstein thought he was such a loser. He wrote a letter to his family saying that it would be better if perhaps he was never born. Nobody was talking about the young Albert Einstein.
He worked as a substitute teacher in short jobs in various towns. Einstein's father tried to apply on behalf of Einstein for academic positions. And he wrote to a very famous professor and asked him whether he could use Einstein as a research assistant. But there were no positions available.
His father passes away, thinking that young Albert is a total disgrace to the family.
In 1902, the depressed and despondent young Albert moves to Bern, Switzerland's capital, and begins a career far from science.
One of his friends arranged for Einstein to get a job as a lowly patent clerk in the Swiss patent office.
In this office, on the third floor, Einstein spends 6 days a week reviewing applications submitted by all kinds of inventors to the Swiss government.
Given a patent, you had all this information, and he had to strip it down to the essence. And that honed his skills as a physicist. He would very quickly dash off all the patents that he had to analyze.
He didn't find the work very strenuous. It was not so intellectually demanding.
And it would give him ample time to contemplate the universe.
He never would have been very good at a university, kissing up to a senior professor. He was much better at a stool in the patent office, trying to daydream about what is it like to ride alongside a light beam.
From that job, he would launch a revolution which would change world history.
Einstein's idle daydreams will profoundly change the way the universe is understood. In 1905, in what's been called his miracle year, he publishes in his spare time 4 visionary papers, the first of which answers the age-old question, what is light?
The photoelectric effect. This paper, written by this total unknown, showed that light comes as a particle called the photon. We use that in television, we use that in lasers.
In another paper, the 26-year-old Einstein posits something we now take for granted, the existence of atoms.
People didn't believe in atoms in those days, but he proved that atoms can actually make small little dust particles move in a liquid. And he calculated the size of atoms.
These papers would have been a remarkable career for any physicist, but Einstein is far from finished.
He writes yet another paper with the famous equation E equals mc squared.
At the simplest level, this means energy can become matter, and matter can become energy. The tiniest speck of matter holds potentially huge amounts of energy. Unleashing it requires a nuclear reaction, the sort going on constantly in the night sky.
Ever since people began to look up in the heavens, they would say, what makes the stars shine? But it took Albert Einstein to answer the question. Mass, M, turns into E, energy. That is the engine that lights up the stars.
Today, E equals mc squared is Einstein's most famous equation. But another theory he publishes this same year is more important and more controversial. The special theory of relativity. When Einstein was a teenager, he enjoyed imagining what it would be like to ride a beam of light. Now, he returns to this daydream, and it changes his life.
In the spring of 1905, Einstein was riding on a bus, and he looked back at the famous clock tower that dominates Bern, Switzerland. And then he imagined, what happens if that bus were racing near the speed of light?
In his imagination, Einstein looks back at the clock tower, and what he sees is astonishing. As he reaches the speed of light, the hands of the clock appear frozen in time.
Einstein would later write, "A storm broke in my mind. All of a sudden, everything kept gushing forward."
Einstein knows that back at the clock tower, time is passing normally. But on Einstein's light-speed bus, as he reaches the speed of light, the light from the clock can no longer catch up to him. The faster he races through space, the slower he moves through time. This insight sparks the birth of Einstein's special theory of relativity, which says that space and time are deeply connected. In fact, they are one and the same, a flexible fabric called space-time. Sitting alone on a city bus, Einstein believes he has glimpsed a secret of the universe. In 1907, Einstein agrees to write a new article explaining special relativity. But when he re-examines his theory, he finds it seriously limited.
It was called special relativity for a reason, and that was because it really only dealt with moving at constant speeds.
In other words, Einstein's special theory of relativity only applies to a special case, an object moving in one direction at a constant speed. But Einstein wants to understand the real world, and the real world doesn't work that way.
Einstein realized that his theory failed for accelerations. But in our universe, everything accelerates. On a bumpy road, jet airplanes, on a subway car, everything's accelerating. So there was a defect in special relativity.
On Einstein's imaginary journey, if his speed varies at all, his theory, his notion of how objects behave in time and space, falls apart.
His scientific mind wants it to apply to all cases.
Einstein knows that for his theory to work, it has to account for everything in the universe. And that includes the pervasive and invisible force that holds everything together.
Gravity. Gravity is everywhere. Gravity holds us to the floor. Gravity holds the sun together, the solar system together. Where was gravity in special relativity?
Einstein wants to expand his special theory of relativity into a general theory of relativity, a theory that will explain not just time, but also gravity. He realizes he will be fighting more than 2 centuries of scientific thought, and his hero, Sir Isaac Newton. It's 1907, and the 28-year-old Albert Einstein is still a patent office bureaucrat. It has been 2 years since he published his special theory of relativity, and the ambitious Einstein decides to advance an even more radical interpretation of the universe, a general theory of relativity. Doing this will require him to take on his scientific hero, Sir Isaac Newton.
In Einstein's time, Isaac Newton was God.
Newton was the founder of modern science. This is the actual first edition of Newton's Principia Mathematica of 1687. This priceless artifact is the very, very famous book which became the foundation of universal physics for centuries, until Einstein upset the apple cart.
It has been almost 250 years since the apple fell from the legendary tree on Isaac Newton's estate, giving Newton the inspiration to formulate his law of gravity.
Newton said that if an object falls, it's because there's a mysterious force called gravity pulling it down. But you know, Isaac Newton himself was not satisfied by that. Objects move because they're pushed, not pulled. Objects move because they're pushed. So what is pushing this? Newton didn't know. So Newton simply threw his hands up and said, I don't know. So I'm going to invent something called gravitational pull. And Einstein said, no, this theory can't be right.
He was prepared to simply go, I really want to solve this problem. I want to really understand the whole universe.
Max Planck said to him, you can work on gravity if you want to, but there are two problems.
You're not going to be successful. The problem is too hard.
And if you do, no one will believe you.
It's an extremely difficult task. It's not clear where to begin or how to go about doing it at all. Ultimately, the thing that gives him that clue turns out to be his old faithful way of reasoning, the thought experiment.
It's what you and I would call daydreaming, but he gets to call them thought experiments because he's Einstein.
He's in his office at the patent office, looking out at the window, and he imagined a man working on a roof. And he begins to wonder what would happen if one of those men were to fall off the roof.
And then he had the happiest thought of his life, the inspiration of the ages.
He had a vision. The man will not actually be feeling his own weight.
He would be weightless. And then he imagined, if you're in an elevator and somebody cuts the cord, what happens to you? You fall. But the elevator falls at the same rate you do, so you are weightless inside the elevator. So then Einstein got it.
It's as though gravity's been switched off. What's really going on?
There is no such thing as gravitational pull. The Earth has curved the space around me, and space is pushing me into this chair. Space itself can be curved.
That's crazy sounding.
Space is adjustable.
It's actually malleable. Space and time are malleable.
It's this flexible thing that can be twisted.
You bring an object into space and it distorts the space around it.
Why does the Earth go around the sun? Most people would say, well, the sun's gravity is yanking the Earth toward the sun in a circle. Wrong. The Earth is going around the sun because the sun has warped the space around the Earth, and space is pushing the Earth toward the sun. He had a new theory of gravity, a new theory of the universe.
Einstein publishes his ideas about gravity. At the same time, his work on the atom brings him increased attention. As a result, in 1911, he's offered a position as a full-time scientist at the University of Zurich. The 32-year-old patent clerk finally leaves Bern to become, for the first time, Professor Albert Einstein.
People start realizing that those miracle year papers of 1905 are probably right. And he starts getting invited to the Solvay conferences, which are the gatherings of the greatest physicists in Europe.
Convened by the Belgian philanthropist Ernest Solvay, these conferences bring together the greatest scientific minds in Europe, and Albert Einstein is among them. In fact, he's the youngest professor there. It's 1911. For 4 frustrating years, Einstein has struggled to perfect his general theory of relativity. His theory won't be accepted until he can demonstrate this radical concept. Suddenly, he is struck by an idea. If he can shine a beam of light through an area where space is curved, then according to his theory, the beam of light will actually appear to bend.
Light only knows straight lines. What's bent is space.
What could have enough gravity to bend light? So much. Well, what about the sun?
300,000 times more massive than the Earth, the sun is the perfect object for Einstein's experiment. But how can anyone shine a beam of light around the sun?
He says light from a distant star, as it passes right next to the sun, and the sun's gravitational field will be bent.
Because space is bent around the sun.
But even if Einstein is right, he'll never be able to see it happen because the sun is just too bright. Except,
when is the sun covered so that we can see what's around it without being blinded by the light? that only occurs during a total solar eclipse.
Here's the sun, and it's blocked by the moon, and suddenly all the stars come out. He figured if you have the sun here, and there's stars way back here, and the light's coming in toward you, it will bend slightly. So to your eye, you think that the stars had gone out like that.
Light going around the sun. That's something that even his mother could understand.
Nobody actually was willing to say without doubt this is the truth until somebody can prove it by taking a picture.
So who do you turn to? You turn to the astronomers, the astrophysicists. Our laboratory is the entire universe.
By 1912, Einstein believes he is finally on the verge of proving his long percolating and provocative theory.
He publishes this revolutionary prediction and puts the call out to the astronomy world. Go out and measure. He said, go to an eclipse and do this observation. People said, we have to redo the test.
In September of 1922, a total solar eclipse will be fully visible in Australia, and William Wallace Campbell sees an opportunity to set things right once and for all.
He started making plans to completely redo his equipment.
Completely redesigned entirely with this measurement in mind. This was the Cadillac of Einstein effect measuring equipment.
The first eclipse point was the very, very, very westernmost part of Australia, in a place called 90 Mile Beach.
Campbell, now in his third expedition, is much better prepared. He gets perfect results.
And they showed, I think, 92 stars that the Einstein effect was not only there, but it behaved as Einstein predicted, very clearly, very unambiguously. This is one of the lenses which confirmed the theory of relativity. The light actually passed through this lens and actually fell on this plate. This stuff is way cool. I mean, this is the heart. The stars that could be seen around the eclipsed sun, here highlighted, showed just the deflection predicted by relativity.
They nailed it. Einstein was so right.
It is a proud personal achievement for Campbell and a landmark moment for science.
The Lick Party finally succeeds, gets extraordinarily good results, and resoundingly corroborates Eddington's 1919 measurements.
Now, who was the first person that Campbell sent a cable to with the result? Albert Einstein. He wanted Einstein to know, boy, did we vindicate you. Boy, did we show that Eddington was right, despite what all the scoffers are saying. For Einstein, this was a tremendous triumph.
The eclipse expedition gives us amazing proof of something that looks theoretical, and yet it's very much part of our lives.
They showed that space-time around the sun was curving.
There's a whole new way of thinking about how gravity works.
How strange is that? That's completely against our intuition. But it's what the data showed, and you cannot argue with the data. Nature agrees. Yes, Einstein, that's a beautiful theory. You're right.
Finally, 15 years after he first proposed his radical general theory of relativity, upending more than 2 centuries of scientific thought, Einstein is victorious and vindicated. Almost.
You know, it's not until 1922 that they finally announce his Nobel Prize. And one of the ironies, he never gets it for the theory of relativity.
Instead, Einstein receives it for the first of his Miracle Year papers, which describes the photoelectric effect. This work becomes the foundation for quantum mechanics and unlocks the secrets of the atom. As the world recovers from a horrific war, it embraces a man with the obscure occupation of theoretical physicist and turns him into a global icon.
Here you have the end of the most destructive war in European memory.
And here this pacifist saint comes along with a wild halo of hair, piercing eyes, and people on all sides of the Atlantic in Germany and in England and in America could all celebrate him as a man of peace, but also somebody whose science transcended the horrors of war.
That's where the emotional resonance of his accomplishment came, I think. And that's why people seized on him, not just as a smart guy, but as a symbol, maybe an all-purpose symbol of what humanity can do well in the context of what humanity has clearly done so terribly.
His story, the solo scientist who turns the world upside down, is enticing. Alone in his studio, using only his mind and a pencil, Einstein made bizarre discoveries as intriguing to the public as the most talked about music and movies of the day.
He put together elements of the universe that others had not imagined would fit together. The general theory of relativity is one of the greatest achievements of the human mind.
If you think about it, the entire modern age, the age of laser beams, telecommunications, satellites, that age was opened up by the work of Albert Einstein. For example, black holes and neutron stars and the Big Bang itself, you cannot describe them adequately without Einstein's theory of general relativity.
It is beautiful and simple and profound. And all the best theories of the universe are just that.
Einstein dies in 1955 at the age of 76. But more than a half a century later, the man and his theories continue to capture the popular imagination and to inspire.
Here was a man, because of the power of his intellect, the sheer power of his mind, was able to rise above poverty, rise above war and strife, to become one of the great figures in all of human history. And that was an inspiration, because you don't have to be born handsome, you don't have to be born with muscles, you don't have to be born that way. You can achieve it by the sheer power of intellect. And for me, that's always been a shining beacon.